the angular momentum of the disk of the rotor. Okay. So this is, we will see the details of this subsequently, but what I wanted to show you in this graph is that you can show the transactions of power, and we'll attend to each of these aspects in a very gradual manner. So right now this may seem to be extremely cluttered and it may seem to be too complicated, but don't worry about it. We will go step by step through each of these parts and you will be able to understand everything. So let me just summarize about, or rather just let me provide you with the introduction. The technique which we are going to study was developed by Professor Henry Painter, and it was actually revealed in the form of publication and disseminated sometime in 1959. And Professor Henry Painter, then he was just an assistant professor, but he is credited with the invention of this technique of bond graph. And this is how he looks. We will see other photos of him also later. But he is actually credited for representing the pictorial grammar for physical system dynamics. So modeling physical systems in the form of graphs or pictures, okay, representing the dynamics in the form of pictures with complete mathematical information embedded in the picture. So that credit, the credit for the grammar, the pictorial grammar, goes to Professor Henry Painter. The important contribution of Professor Painter in this is the development of the representation of the power bond. Now the power bond is it's just an arrow. You saw that it's a half arrow, and it's actually different from a full arrow, a signal arrow. A signal arrow carries information of just one variable. Okay, so the power bond or the power arrow, which was actually designed by Professor Henry Painter, it represents the power transaction as a product of two variables, an effort variable and a flow variable. And whenever you have a transaction of power in any energy domain, in the physical world, you require these two variables, an effort variable and a flow variable. And we will see that what these effort and flow variables are in different energy domains. The next point which Professor Henry Painter contributed was the basic elements of this pictorial grammar. And we have just 9 elements in bond graph. And with the help of these 9 elements and the power bond, we can model physical systems in multi-energy domain. Okay. So here you have elements, and these elements are further divided into junctions. We have 2 junctions, we have 3 elements, and we have connections. We will understand each one of them subsequently. And the most important aspect of this bond graph is the representation of cause and effect, or input and output, and representing that very elegantly on the bond graph itself. So just summarizing, why are we going to understand bond graphs, bond graph modeling? Why? First of all, we will have graphical representation of the dynamics of the system, because it's going to be easier to understand dynamics of the system in a graphical form. Secondly, this method is going to offer us insight into the physics of the system. We are not going to deviate from the physics of the system. Okay? It can be applied uniformly to multi-energy domains. We have already mentioned about this. And we will have interaction of power between elements of the system. Okay? We can represent the interaction of power between elements of the system. The representation of cause and effect, input and output on the graph itself. We will be able to algorithmically derive system equations in a particular form, and this form is very useful because it's going to help us to integrate, to simulate our model. Okay, we have differential equations and we will be able to integrate these differential equations numerically. So this form is very important, and of course we are not going to do it manually. We are going to allow the computer to do that for us. This forms also the basis for modern control theory, and I am sure that even in textile engineering you have control related applications. And coding for simulation. So we will be studying how systematically one can do coding for the simulation directly from the bond graph without even deriving system equations. The best aspect of bond graphs is that you can modify the bond graph. If you would like to add some more phenomenon to your system, you can always include additional dynamics. You can modify the bond graph, you can append or you can delete part of it, suppose you are not interested in focusing on a particular phenomenon. Okay? So you can isolate it. So all these things are possible for you using this technique. And it helps in development of control strategies and diagnosis. It has also helped in the development of several strategies which have been listed. It's also very effective in fault identification and diagnosis. Okay, and
we have only five.
Okay. And there are several software available in order to handle bond graph. One of them is CAMG. The most popular software perhaps is 20Sim, which is by the 20 University in Netherlands. And of course, I am proud to say this, that it's perhaps one of the best software, most capable, that is Symbols, and it's called by the name of Symbols Vista nowadays. Earlier model was Symbols Shakti. This is credit goes to an Indian group at IIT Kharagpur for the development of this. But all these software use the same idea, okay, the same tools and the same grammar. There is a software AMESIM, and there are several software. In fact, all this started with Professor Ronald Rosenberg, who was a PhD student of Professor Henry Painter at MIT, and he came up with a software called NPort, and with the NPort software, that was the first software for handling bond graph. You could derive equations from a bond graph, and that was in the good old days, maybe around 80s, 90s. But in our course, we will be doing our modeling, our simulation using MATLAB. Okay, you could use MATLAB or you could use Skylab or other clones of MATLAB. But because we have got our routines already written in our examples already coded in MATLAB, and I suppose many of you are familiar with MATLAB. It's a very commonly used general purpose programming language for mathematical requirements, and so MATLAB is quite convenient. It's easy to program, and best is that all the control is with the modeler. So if you purchase, first of all, if you depend on the software which I mentioned earlier, you have to pay for them, and they are not freeware so far. Maybe you can download the demo versions, but then that's applicable only to a few variables. You cannot save your files, you can't print your files. So there are certain restrictions imposed on these demo models, and so the full capabilities of your modeling are not visible. And of course, with our own coding, with our own understanding of how to code this modeling of physical systems, it becomes easy for us to modify, it becomes easy for us to append, okay, and carry out all other tasks with the help of MATLAB. Okay, so you could use MATLAB or Skylab. There are marginal differences. They are not 100% compatible, but certainly you could make use of any one of this. So with this, I think, shall I take a few?
Only, I think, only 3 minutes left. You can continue.
So with this, I am going to introduce to you the power transaction through a bond. This is the arrow which was conceptualized by Professor Henry Painter, and of course there is a long history which he has provided about it, which is available online also. And this is carrying the information of power. Now power requires two variables to be represented. So this arrow is representing the transaction of power, but you require an effort variable which is represented by E, and it can be represented at any time t, and at the same time you also have to have a flow variable which we will represent using F. Okay, so power requires two variables, an effort variable and flow variable. In different energy domains, power can have different forms. So the effort and flow variables would be different. So here you have the effort variable, say in the electrical domain. You have the potential difference, which can be taken as effort. You have the flow, which can be taken as current. You have force in the mechanical domain and velocity. You have pressure and the volume flow rate. You have temperature and entropy flow rate. You have torque, you have angular speed. So you have corresponding to the energy domain, but in every energy domain you have an effort variable and a flow variable, and always the product of these two is a scalar, which is power. Okay, so with the introduction of this power bond, I suppose we can take
Only 1 minute, so you decide.
Okay, so if you
To time. Otherwise,
that's okay, that's okay. A minute here and there, it's perfectly okay.
1 minute.
So
You will stop or?
yeah, we can before we go to the elements, we can take a break here.
Thank you, Professor Anand. And I am requesting all participants for a cup of tea. You will be sharply here at 6:40. 20 minutes for tea break. Okay. We'll start at 6:40.